Okay, welcome once again, one and all. So, in this lecture, we will discuss the method of maximum likelihood estimation. Okay, so actually, this lecture, this is the part of the series in estimation. Okay, so up to so far, we have discussed unbiased estimator, then consistent estimator, then most efficient estimator. Okay. So now this is a maximum likelihood estimation. Okay. So actually at present, we are discussing the characteristics of a good estimator. By now, we have discussed the three characteristics, which were unbiasedness, then consistency, and then efficiency. Okay. And now this is a MLE, maximum likelihood estimation. Okay. So now here, actually, the crux of this method is here that in this method, MLE, we try to find or estimate that value of unknown parameter theta. So first of all, this whole estimation, this the chapter of estimation or the concept of estimation, it is about finding the values of unknown parameter. So this I have started from this fact onwards. Okay, that this whole concept of estimation, it is about what? It is about finding or estimating the values of unknown parameters of the population. Okay, so here we have a population. Okay, and the population follows a certain distribution. Usually it is known that a population follows a certain distribution. Okay, so for that population distribution, because every population has some parameters, and those parameters are not known to us. Okay, so here now, and now in MLE, we try to find or estimate that value or those values of unknown parameter theta, which maximizes a certain function. And this function is known as likelihood function. And the symbol is L. Okay. So that's why this method name is maximum likelihood estimation. Okay, so I repeat that in this method of MLE, maximum likelihood estimation, we try to find or estimate. We try to find or estimate those values of that value or values of unknown parameter theta, which maximizes likelihood function. Okay, and first of all, what is this likelihood function L? So this L, actually it is the product of pi product of fxi theta and I1 to n. So basically this is f at x1 theta into f at x2 theta going on up to f at x and theta. Okay. So, so what is this fxi theta? Actually, this is the PDF. Okay. So this is the PDF of the distribution. PDF of the distribution, probability distribution, which the population follows, which the given population follows. Okay. So I have already stated that usually, not always, usually it is known that the population follows which particular probability distribution. So this F, it is the PDF of the same distribution. Now, what these xi's represents? Actually, these xi's, they represent our sample observations. Okay, so small x1, x2, going on up to xn. Okay, so xi, I am mentioning xi, and obviously here I from 1 to n, I from 1 to n. Okay, so these are our sample observations. Okay, and now what is theta here? Theta is the unknown parameter, okay, of the population. Now, this theta, it may have a single component. Okay, this theta, it may have a single component, but it may have more than one component. For example, this theta, it may have, say, theta 1, theta 2, going on up to theta n, means it may have n components. Okay, if theta is single, is having single component, it is having only one component, we call that theta is a scalar value. Theta is scalar valued. And if theta has components, okay, then we call it vector valued parameter. Okay. Now, example, suppose our the population has Bernoulli distribution. Okay, the population has Bernoulli distribution. A population is having Bernoulli distribution, then we know the PDF, the probability distribution function. This is given by uh, fx, okay, that is nothing but p raised to power x and 1 minus p raised to power 1 minus x. Okay, so this is the PDF, okay, or actually this is probability mass function. Okay, so here what's the meaning of PDF? Please mind, it is not actually it is probability distribution function. This PDF, it is probability distribution function. So actually, probability distribution function, it is of two types. One is probability mass function and one is probability density function. If our random variable is discrete, okay, so then the probability distribution function, it is known as or called as probability mass function. And if our random variable is continuous, okay, then the probability distribution function, it is known as probability density function. Okay, so this is the PMF of the Bernoulli distribution or Bernoulli population. Now, this population, it has only one parameter. What is that parameter? It is P. P is the parameter. Okay, and but further, what's the meaning of P? This P, it is the probability of success. Okay, so now here, what is our parameter theta here? The parameter theta here is only P. Okay, means the parameter has only one component. Okay, so this is the case, and similarly, suppose our population is having, say, Poisson distribution. Then what will be our this PMF? So that will be given by E minus lambda, lambda raised to power x. Okay, here it is product, divide by x factorial. So here, once again, what is the parameter? It is lambda. So here theta is our lambda. So even here, theta has only one component. Okay. So these PMF I have discussed in the previous lectures also. Okay. So for more detail, please watch those if you are interested. Okay. Now, suppose our population, it is having normal distribution. Suppose our population is having normal distribution. So in this case, what will be our this fx? Okay, the PDF, that is 1 by sigma root 2 pi E minus half, actually 2 and actually sigma. Okay, I should write here that it should be E minus half. Yeah, minus half x minus mu divided by sigma whole square. Okay, so this is the PDF of normal distribution. Actually, this particular variable, x minus mu upon sigma, it is a special variable. We give it a very standardized symbol, that is z or z. It is x minus mu upon sigma. Okay. So actually this Z or Z, this is what we call standard normal variate. Why? Because it always has mean zero and variance or standard deviation is one. Okay. So what is this mu here? This mu, it is the expected value of x. Okay, the same x. Okay, this x. Okay, if you are not here, so here say capital X. Okay, so it is expected is this. Okay, and the standard deviation of x is sigma. Okay. So now this mu, it is the expected value of x, mean value of x. Okay. And what is this sigma? It is the standard deviation of the same x. Okay. Now, if our population is having normal distribution, okay, so this will be the this one. It is the PDF. Now here we know that the normal distribution, it has two parameters, mu and sigma square. So what is theta here? So here theta, it is having two components. So I write here theta, it is having two components. One is mu and another is sigma or sigma square. So now here theta has two components, theta 1 and theta 2. Where what is theta 1? It is mu, and what is theta 2? It is sigma square. Okay. So this is the meaning here. Okay. So now, as it is mentioned that this method of MLE, it is just similar. Obviously, it is just similar to the method of finding those values of independent variable x, which maximize the dependent variable y equal to fx. Okay. So because of this thing, our equations, we will require certain equations to find this theta. Those equations will be dl by d theta equal to 0. This will be the one means expression that we will be requiring. Okay. So, so this will be first, actually this equation we require, and then d square L by d theta square. It should be negative. Okay. Why so? Actually, in the I think by your previous knowledge of maxima or minima in your previous class, when you were finding the minimum and maximum values of a certain function y equal to fx, you were using two. One is two expressions basically. One was d by dx of this fx, y or fx equal to 0. And then second was the double derivative. The double derivative of fx, it should be negative. Okay. So here actually first equation, it gives us the stationary points. The first equation, it gives us the stationary point. Actually, it gives us those values of x. This equation, it gives us those values of x, independent variable x, which possibly maximize or minimize fx. Okay, stationary points, or we call them critical points. Okay, and at those points, what do? You find the value of second derivative, and if the value of second derivative, it comes out to be negative. Okay, if it comes out to be negative, then you say that that value of x is the point of maxima. Okay, so I repeat here. Yes. So from first equation, what we will you were having that x equal to say x1, x2, going on say xn. So what are these points? So these points, they are stationary points or critical points where possible maxima or minima can occur. Now, at each such point, x1, x2, xn, what you do, you find the value of second derivative of fx or y. Okay. And if any such point means at any such point, if the second derivative, it comes out to be negative, then you say that point means that value of x, okay, it is a point of maxima, okay, for this function. So here, once again, if you look carefully, here we are finding those values of x, the independent variable x, independent variable x, which maximize fx. Okay. So in this MLE, what we do? We try to find those values of theta, the parameter theta. Okay. Unknown parameter theta, which maximize L. It is so, I think you understand this now. So that's why these similar expressions will be used here. So just like this case, okay, we have this case. I repeat, just if you, so just like finding those values of x, okay, which maximize fx. Here we try to find those values of theta, okay, which maximize L, the likelihood function. Okay. So that's why the method's name is MLE, maximum likelihood estimation. Okay. So now, what is this L? It is the product of these PDFs. Okay. So one thing here, actually, there is a certain difference in the notation. So here I am writing the notation in terms of sample observations, xis and theta. Okay, but here I have not mentioned theta, so we can write this equal to say fxp. Okay, and this fx lambda, and this it is fx mu and sigma or sigma square. And what is this pair? This pair is our theta. Here, theta is having two components, and here theta is having only one component. Okay. So this is the actually working principle. This is the working principle of MLE. Okay. So I think this thing is clear by now. If not clear, then uh, d by dx of fx equal to 0 and d square by dx square of fx, it is negative. Okay. So here these two, they give us those values of x. These two, they give us those values of independent variable x, which maximize fx, the dependent variable fx. And d by d theta of L, okay, and d square by this. Okay, wait. D square. This is negative. So these two expressions, they will give us they will give us those values of unknown parameter theta, those values of unknown parameter theta which maximize L, the likelihood function. Now, if theta is only scalar valued, means it has only one component, then we use this symbol d by the d theta, the ordinary derivative. But if theta has two components, then we use this notation, that is curl by curl theta, means partial derivative. Okay, so partial derivative here and even here. Okay, theta is here. If our theta, it has two components, means more than one component. So theta is the ith component. So obviously here we have to differentiate L with respect to each component. Okay, and obviously with respect to each component, obviously natural thing that here theta will have the components. So we have to, if I have to find theta, okay, so what I have to do? If I have to find or estimate theta, I have to find every component of theta. Okay, so here we try to find means if theta has n components, then we try to find or estimate. We try to find or estimate all the components of theta because in order to find or estimate theta, we have to find or estimate all the components of theta. Okay, so now we will try to find or estimate all the components of theta, okay, which maximize L. Okay, so that's why we will be using these notations also. And on natural thing, so we have to differentiate L with respect to each such component of theta. And then uh, in practical questions, rather than maximizing L, I repeat, in practical means in our questions, rather than maximizing L, we will be maximizing log of L, the log of L. Okay. Why so? The reason is simple. Actually, in our questions or practical situations, finding the derivative of L, finding the derivative of L with respect to the parameters. With respect to the parameters, it will be a typical thing. Means the calculations for finding the derivatives of L, okay, they will be bit complicated. But finding the derivatives of log L, they will be comparatively easy. Finding the derivatives of log L with respect to the components of theta, it will be comparatively easy. This we will see very soon, okay, and I will point it out also. So, curl by curl theta, sorry. Mm, so, curl theta I log of L equal to 0 and curl square curl, and sorry, it should not be this one. Here it should be uh, log L. Okay, log L, and here curl theta I square, it is negative. And here one property we are using, those values of theta or theta I, those values of theta or theta I which maximize L. Okay. The same value of theta I or theta I, they also maximize log L. I repeat, actually log function is increasing function. Okay. Uh, Means if x1 is less than equal to x2, then log of x1, it will be less than log of x2. Okay. So since it is increasing function, so those values of theta I which maximize L, the same values of theta I will also maximize log L. Okay. And please mind this, although it is log L, but it is with base E. There are two logs which we use very often. One is LNL. Actually, what is LNL? Natural log L, which is with base E. And there is another log that is with base 10. This we call common logarithm. Okay. Although I am using this symbol, but please do not do not take it as that here it is with base 10. So actually here it is with base E. This is with base E. So it should be LNL. Okay. So actually, just to actually this notation, it is not used by the most of the authors. Most of the authors, they use this notation. So I will be using this one also. And moreover, to work with this LNL, it may create some confusion. Okay. So that's why I will be using this notation. But once again, this log, it is with base E, not with base 10. Okay. Now, obviously, if you look at this equation, okay, what it will give you? It will give you 1 by L and curl by curl theta I of L equal to 0. Because L, it is a function of theta, obviously, because you can see what was L? It was product of fxi theta, okay, I 1 to n. Then wait. Surely, then obviously L is a function of theta because, okay, theta is the variable here. Okay, it is unknown variable. And xi, once the sample observations are known, xi, the sample observations, they are known. So xi is will no longer be a will no longer be a variable. When once the sample has been taken, okay, then these xi's, they will no longer be a variable. So what is the variable here? Theta, the unknown parameter. So this L, it is a function of theta. So I think you know that how we differentiate log of f theta with respect to theta, the log of f theta. So I write here, just wait, that curl by, or if I curl theta with respect to say some function, if I use another, say capital F theta, so sorry, log of f theta. So yeah, wait. So here log of f theta, some function of theta. So capital F theta, capital F. So it is 1 by f theta, okay, into curl theta of f theta. Okay. So the same thing we are using, that here this capital F theta, it is nothing but our L. This is our L. Okay. Now, let's see a question which is the more important for us. Uh, so we have a random sample from normal population. We have to find the MLE for mu when sigma square is known, means we have to find that value of unknown parameter mu, which will maximize L. First of all, it will maximize log L and hence L. Similarly, MLE for sigma square when mu is known and the simultaneous estimation. Actually, in first case, sigma square, the population variance is known. Since it is known, it will not require any estimation. If sigma square is known, then obviously it will not require any estimation. Obviously, naturally, we estimate that thing which is unknown. Okay, we estimate that value which is unknown. The value which is known, the parameter which is known, obviously there is no need to estimate that. So in first case, sigma square is known, so we have to estimate mu. And how we will estimate mu? Mu, the population mean. We will estimate or find mu. We will estimate or find mu, which will maximize log L and hence L. Okay. And in second case, uh, since mu is known, so mu population mean, it will not require any estimation. So we will find or estimate that value of sigma square, population variance, which will maximize log L and hence L. And in third one, since both will be unknown, mu and sigma square, so here we will try to find or estimate those values of mu and sigma square which maximize log L and hence L. Now, so first thing L, what is that? Product fxi theta I1 to n. So what is this thing now? It is product 1 by sigma root 2 pi with this. Yeah. E minus half, okay, then xi minus mu divided by sigma whole square, okay. So obviously it is I1, 2, and so this thing now, it is 1 by sigma root 2 pi E minus half x1 minus mu upon sigma whole square, then 1 by this E minus x2 minus mu and 1 x. So here, what is this value? The first term. Actually, this first term, it is the value of this function. Okay, it is the value of this PDF when our I is 1. So here I is, you can say here I has been substituted 1. What is this term? It is the value of the same PDF when I has been substituted 2. Going on, what is this term? It is the value of this same PDF when this same it is substituted n. So what is this pi? Pi stands for product. Okay, just like summation. Summation stands for sum. The pi, it stands for the product. Okay, basically, what are these terms? These terms, they are the values of the PDF of normal distribution at first sample observation, at second observation, and at the nth sample observation. I repeat, what are these terms? These are the values. These are the values of this PDF. Okay, the PDF of normal distribution at first sample observation, at second sample observation, so on up to nth sample observation. So this is now 1 by sigma root 2 pi. So actually you will require the expression of this normal PDF. So 1 by sigma root 2 pi. Okay, and here it will be raised to power n. Why? Because here this term is there, into here this term is there, into so on, here this term is there. How many times it is here? Means how many times it is multiplied with itself and times. Now, E minus half and summation xi, wait, xi minus mu upon sigma whole square and I1 to n. So E exponential is there. Here it is raised to power y1. You can say this is our first term, y1. And here it is e raised to power y2. Okay. And going on here, it is e raised to power yn. Obviously, it is depending upon our 1, 2, because here I am saying it is y1 because here it is the first sample observation. Here it is y2. Here it is the second sample observation. Here it is yn. It is the nth sample observation. So this is actually e raised to power y1 plus y2 plus so on yn. So this is nothing but the e raised to power summation of yi. Okay, so I have done the same. So it is 1 by sigma. Okay, this thing. Now taking log on both sides. So log of this sigma, and here it is n and e minus half, and this whole term of this xi minus this one. Okay. So now this is log of sigma and this one, and plus log e minus half and summation the same. Okay, so this term is our A, say this is capital A, and this term, say it is capital B. Okay, this term is capital B. So what is log of A into B? The log of A into B. It is log of A plus log of B. Okay. So here I'm not writing it over and again because here this term xi minus mu by sigma, this term will be here. Okay, but in exam, please do not do this. In exam, please write properly. So now, this one actually it is 1 by sigma root 2 pi. This is whole here. Here it is since it is in denominator, and once it comes to numerator, so here it will be minus n. Okay, and now this minus n it can come here. So minus n log, and moreover it will be sigma plus log of 2 pi and raised to power 1 by 2. Okay, so I'm writing this one. So once again, this is A, this term is A, sigma, and this root 2 pi is B. So log of A plus log of B. And actually 2 pi, it is under the square root. So that is nothing. We can write like this, the square root. This term now, this term, it can come here. Okay, actually a log of x raised to power, say m, this is nothing but m log x. So minus half and summation, okay. The same thing here into what? Log of E. Now, this thing minus n, actually 2 by 2 log sigma means here multiply divide by 2, okay, and then plus 1 by 2 log 2 pi, log 2 pi means this 1 by 2 will be here, and minus half, and this summation, okay, summation of this term, but will be log e. Oh, so here it is base e. I told you na that here it is with base e. So what is log e to the base e? It is 1, because log of, say, if I ask 125 to the base 5, what is that? It is 3. Why? Because 5 raised to power 3, it is 125. Okay, so log of e, because e raised to power 1, it is 1. So now, here, this 2, okay, this 2, it can go here. It can go here. So it is minus n by 2 log of sigma square, okay, and minus n by 2 log of 2 pi minus half summation xi minus mu whole square, and sigma square I can take outside. Sigma square I can take outside, because actually here the sigma square was in the denominator, but this summation is with respect to I1 to n. So this sigma square, it is a constant with respect to this summation. So that's why it can be taken outside the summation. So this is our log of L. Okay. Now, here, if you have observed that I have multiplied n also, please wait. Yes. So here I have multiplied this n also. So now, first case, wait, please. So now, curl by curl mu of log of L. Why so? Because in first part, I want to find that value of unknown parameter mu. In first part, I want to find or estimate. I want to find or estimate that value of unknown parameter mu which maximizes log L. Okay, or hence L. So that's why derivative of log L with respect to mu. So the first term, it is totally constant with respect to mu, so its derivative will be 0. Even second term, you can see, even it is totally constant with respect to mu, so its derivative 0. Now, the third term, if you see carefully, this one, here, this is the function. Here, this is the function which is mu. So how you differentiate if I talk about d by d mu of some function of mu, okay? And whole is to power n. So that is actually n f mu, okay, n minus 1 into what? Into the derivative. Wait. So derivative of this function of mu and its derivative with respect to mu. Okay. So here, yeah, it is n minus 1. So summation twice xi minus mu 2 minus 1 into its derivative. So what is derivative of xi with respect to mu? 0. And derivative of mu is 1. Okay, so this is the derivative. Now you see this thing here. If I ask you what calculations are easier, differentiating log L with respect to mu, differentiating log L with respect to mu, or differentiating L. So what was our L? You can see here it is L. So just wait. Mm, Yes. So this is you can see this is your L. Okay, this is your L. That 1 by sigma root 2 pi whole raised to power and e raised to power minus half. Okay, here product obviously e raised to power minus half, all that. So the derivative of L with respect to sigma, is it easier or the derivative of log L? Log L, you can see. Okay, so obviously the derivative of log L is easier. So that's why rather than maximizing L, we maximize log L. So now put this equal to 0 and you can see actually this minus and minus, this minus, it will be plus, this 2 cancels out. Okay. So what we have actually 1 by sigma square and summation xi minus mu and I1 to n. I1 to n. So this is the actually first derivative. This is the first derivative of log L with respect to mu. And this put equal to 0. So this sigma square, it will go to this side. So summation xi, okay, minus summation mu, that is equal to 0. So summation I1 to n, and even here I1 to n. Okay, just wait, please. So here I1 to n. Now summation xi, okay, and this is now n mu. Why? Actually, what is this term? We are adding a constant. Summation means adding. We are adding mu. Mu is a constant. Okay. So we are adding a constant. How many times? N times. So that is n mu. Please mind mu, since mu is a mean, it is a constant. Okay. So similarly, sigma square, okay, even it is also a constant. And moreover, I have shifted this term to this side also. So from here, what will be mu? Mu will be summation xi upon n. And what is this summation xi upon n? This summation xi upon n, actually it is nothing but our sample mean. Because sum of the observations divided by number of observations, this is sample mean. So here, this is the value of mu, the value estimated value. So here I will put cap. So this is this x bar sample mean. It is the estimated value of mu, which will maximum, which can maximize log L. So for that, what we have to do now? We have to find the value of second derivative. Okay. So the value of second derivative, it must be 0 at this value. Okay, means this mu equal to x bar. So now 1 by sigma square and summation. So this curl curl mu square by log L. Okay. So this is this thing. So this was the first derivative. And now 0 minus 1, I1 to n. So what is derivative of xi? 0 with respect to mu. And derivative of mu is 1. So this is now 1 by sigma square. Now what is 0 minus 1? 0 minus 1 is minus 1. 0 minus 1 is minus 1. So you are once again, you are adding minus 1. How many times? N times. So what will be that? Minus n. And this is always negative. Why? Because what is sigma square? Population variance. Actually variance and standard deviation. Okay, so whether it is population variance, population standard deviation, or sample variance, sample standard deviation, they are never negative. And what is n? N is sample size, means how many number of sample observations are there. So here n and sigma square, they are always, they can never be negative. But here there is a minus here. So means this expression, it is always negative. Okay, so this proves that this value, that mu cap equal to x bar. Okay, so this is what? This is the MLE. This is the MLE for mu. Means the maximum likelihood estimated value. The maximum likelihood estimated value of mu is, of population mean is sample mean. Okay. Now here, wait please. Now here, if you observe, I have put a cap over there. Actually, what is the meaning of this cap? That this value, this x bar, it is not the exact value of mu. Okay. It is not the exact known value of mu. Actually, this is the rough estimated value. Although I should not use the word rough, that this is the estimated value. It is not the exact known value. Okay. So this is the meaning of this cap. So now what was the second part? It is curl by curl sigma square of log L. Okay, because now we want to find or estimate. We want to find or estimate that value of sigma square which maximizes log L and hence L. So this is now actually, if you recall back, what was our L, sorry, log L. So you can see this is the first term. Okay. So what is its derivative with respect to sigma square? That is n by 2. Wait, it's n by 2 into 1 by, uh, wait. So here it should be 1 by sigma square. Okay. And what is the derivative of second term? Actually, it is totally constant with respect to sigma square. So its derivative will be 0. And in the third term, if you look carefully, this term, this summation term, once again, it is constant with respect to 0. So here what we have 2 sigma square. If I write clearly, so it is 2 sigma square. Okay. So what is the derivative of this? Actually, look carefully. What we do, we replace sigma square by some another symbol, say y. Replace sigma square by some another symbol, y. So here we are differentiating with respect to y. So here, what is this term? This is log sigma square. So it is nothing but log of y. It is log of y. And what is derivative of log of y with respect to y? That is 1 by y. The derivative of log of y with respect to y, it is 1 by y. So that's why here I have written 1 by sigma square. And similarly here, what we have in this term, if you see, it is actually 1 by y, because you can see it is sigma square, na? 1 by sigma square. So what is derivative of this 1 by y? So what we need here, uh, yeah, we need d by dy of 1 by y. Okay, 1 by y. Wait. 1 by y. Uh, Once again, so actually this derivative, it is now minus 1 by y square. I think you know this thing, the derivative of this. So that's why this is minus 1 by y square, and y square is sigma raised to power 4. Because what is our y? Y is sigma square. So here, uh, 2 raised to power sigma 4. Okay. So you can see the derivative of this term. Okay. The derivative of this term, it is minus 1 by sigma 4. So here, what should I do? So minus, so you can see I am talking about this term. Okay. It is minus. Okay. So minus 1 by sigma 4. So 1 minus from the derivative, 1 minus from the derivative, and 1 minus is already here. So here it will become plus. So here it is remaining summation xi minus mu, okay, whole square. So this is the derivative. And once again, if you try to feel that the derivative of log L with respect to sigma square, the derivative of log L with respect to sigma square, it is much easier than the derivative of L with respect to sigma square. Actually, the derivative of leg L with respect to sigma square, it will be a very tedious job. Okay. So now uh, put equal to 0. And now uh, n by 2 sigma square, that is equal to 1 by 2 sigma 4, and summation just put xi minus mu whole minus mu whole square. Actually, this term, okay, I have taken to this side, only this thing. Now, this 2 cancels, and even this sigma square will cancel. So here it will be sigma square only. And this sigma square, it can go to this side. And this n, it can come to this side. So sigma square, it is 1 by n summation xi minus mu. Okay, xi minus mu whole square. Okay, and I want to n. So now, this is the estimated value of sigma square. So this is the estimated value of sigma square, which will maximize log L and hence L. So that's why, first of all, I will put a cap over sigma square. Moreover, since this mu is involved here and this mu is known, if you recall back in part 2, mu is known. Known means its value will be given to us. And since it is given, that value we can use here. And what are x's? They are our sample observations, and obviously sample observation will be also with us. So with these values, okay, we can find the estimated value of sigma square. Now, one remark here, if you go through any material on MLE, okay, any, whether it is means across the globe, any author, so verifying that the second derivative is negative, verifying that the second derivative is negative, usually it will be missing. I repeat, you go through any lecture notes of any author, okay, across the globe, you will find that verification of the second derivative, that it is negative, it will be missing. Okay, so why it will be missing? For that, although it is not that much part of this series, but still for your knowledge or curiosity, I am showing you. So here, this thing. Here is the reason mentioned that why we skip or we not verify the second derivative condition. So here in regular cases, the log likelihood function. So now I think you understand log likelihood function, that log of L. It is concave. Concave, what's the meaning of concave? It means that its shape is like this log function. So actually its shape is like this. This is called concave. Okay. So in most cases, the log likelihood function is concave, meaning that the second derivative is negative by default. Why so? Because since it is concave, it will never actually come down. It will never come. It will not be the case, means case that it will come down and again goes upside. Okay, means it will go up and up and up. It will go up and up and up. Okay, so here it will attain only maximum value. Okay, it will never be like this case that here it comes down and again it goes on, goes upward. So this thing is never possible. Okay. And this is because the log likelihood function, it is typically a sum of log terms which are concave. Okay, so even here we are having the sum of these log which are further concave. And verifying the second derivative condition, it can be complicated. So this is also another fact. Okay. Now, the MLE is often unique. Even if we don't verify the second derivative condition, the MLE is often unique. This means that even if we are having multiple critical points, I think you understand this critical point. Okay, only one of them corresponds to the global maximum. Okay, so these are the various reasons. Although these reasons, they are not much part of this series within the ambit or within the scope of our series, but just for the knowledge, I have mentioned these. Okay, but still there are some exceptions that non-regular cases, such as the when the parameter space is bounded or when there are multiple local maxima, verifying the second derivative condition is actually crucial. Okay, so these are the reasons, and now coming back. Now in part 3, actually what we need, yes, wait, yeah, wait please. Yeah, what we need, this simultaneous estimation of both mu and sigma square. So basically, curl by curl mu of log L, even this should be 0, and curl by curl sigma square of log L, even this should be also 0. Why so? Because now both mu and sigma square are unknown. And now we need to find or estimate, that value of mu and sigma square which maximize log L and hence L. Okay. So now this equation we have already solved in part 1. And when we solved this, what we had that mu cap, it is equal to the estimated value of mu was sample mean. This equation, this we have solved in part 2. And we got that the estimated value of this sigma square, it is 1 by n summation xi minus mu whole square. Okay. But now this mu, since it is also unknown, But in previous case, it was known. Since it was known, we could have used that known value here. But here, mu is unknown, so we will not have its exact value. We will not have its exact known value. So what we will do? We will use its estimated value. So what is that now? 1 by n summation xi minus x bar whole square. Okay. And obviously I1 to n. And if you have practiced by now or seen the lectures by now seriously, properly, which one must do. Okay, otherwise he will never feel confident in this concept. So this expression, it is nothing but small s square. What is small s square? The sample variance. So now, if our sample is from normal distribution, normal population, then sample mean, it is the MLE of unknown population mean, and sample variance, it is the MLE for unknown population variance. In other words, okay, these this X bar and S here, they are our required MLEs. So now here we have a population whose density function is given by this 2 by alpha square alpha minus x, where x is between 0 to alpha. And what is the alpha? This is the parameter. And obviously this parameter will be unknown. Okay. Uh, okay. And what is the sample size here? The sample size is 1 only. N is 1. How I know? When a sample of unit size, okay, the sample of unit size is drawn from the population. Unit size means N is 1, means we have only one sample observation. We have the only one sample observation, and that sample observation is denoted by X. This X is the only single unique sample observation. Okay. So since here find the MLE for this parameter, since he is asking that find the MLE for this parameter, so means we have to estimate this alpha. Okay. So now L, what is L? It is once again pi f x I theta and I want to n. And what is this n? Please wait. N. Wait, please. So what is this n? It is 1. So actually, so what we will have here, I will have only one term fx1 theta. Okay. And now what is this x1? It is x. This sample observation, it is x. It is mentioned here that x is the sample, single sample observation. What is this theta? Actually, this theta is alpha. The unknown parameter is alpha. And what is this thing? It is 2 by alpha square. Okay, alpha minus x. So this is our L. Log L now. Okay, it will be log of 2 plus log of alpha minus x. Okay, and minus log of alpha square. So here it is A into B. Okay, so log of A plus log of B divide by C. So that's why minus log of C. Okay, and now this two we can it can come here. Okay, so that's why this is now log of 2 plus log of alpha minus x and minus 2 log alpha. So this is log of L. Okay, so what is this L? It is the likelihood function. Okay. So now derivative with respect to alpha. Okay. We need to find or estimate that value of alpha which maximizes log L and hence L. So here it is 0 plus 1 upon alpha minus x and minus 2 by alpha. Log 2, it is constant with respect to alpha. So derivative is 0 and its derivative it is 1 upon this and this one and put equal to 0. So this 1 by alpha minus x equal to 2 by alpha, and then this is alpha 2 alpha minus 2x. So from here, what will be alpha? Alpha will be 2x. Okay. So now what is this value? Actually, this is the estimated value of alpha. It is that estimated value of alpha, which is maximizing log L or L. And actually, what we will do here, the single sample observation, okay, that will be known to us. We will multiply it by 2 and this value, okay, this twice x, it will serve as this twice x, it will serve as or act as the the estimated value of alpha. That estimated value of alpha, which maximizes log L and hence L. Now, is this above MLE biased? So here he is asking, it is being asked that this MLE value, whether it is biased or unbiased. So expected value of this alpha cap, that is expected value of 2x, and this is now integration 2x into what? Into 2 by alpha square and alpha minus x. Uh, wait. So here it will be dx, and x is from 0 to alpha. If you have observed, it is mentioned that x is from 0 to alpha. Okay. So now what is this thing? Actually, in one of the previous, I think in the very first lecture on estimation, I mentioned that expected value of any function, it is nothing but the value of the function into what? Into the PDF, okay, the probability distribution function. And now here it will be integration. Okay, integration. Why? Because here our random variable is continuous. Here x, our random variable. Okay, it is between 0 to alpha. Here x, it is not taking discrete values. X is not taking discrete or countable values. Actually, x is lying in some range. Okay, interval. X is lying in some range or interval. So here obviously our random variable is continuous. And if our random variable is continuous, then we use integration. Okay. So by chance, suppose if I am calculating, say, expected value of, say, 3x square minus 4x. Okay. If I am calculating the expected value of this, then this will be integration of 3x square minus 4x, okay, into what? Into the corresponding PDF, okay, over whatever the range of random variable, means their limits will be according to the range of the random variable. And if your random variable x, it is discrete, then this expectation, it will be summation. Okay, summation of 3x square minus 4x into what? Again into fx. Okay, what will be this fx? This will be probability distribution function. And once again, this summation will be over the range, whatever the given range of the random variable. So what are these? This one, 3x square minus 4x, you can see. Actually, it will be the value of the function, multiplied by what? Multiplied by what? The probability distribution function. Then it is integration. If it is the continuous case, means your random variable is continuous, and it is summation if your random variable is discrete. So now, here we have 4, because this 2 into 2, 4, and divide by alpha square. You can see this alpha square, and but we have now this alpha x square by 2 minus x square, that is x cube by 3, between 0 to alpha. Why so? Because here there is one more x was there. I missed. So this x into alpha, that is alpha x, means alpha x, its integration. Okay. And minus x square. Okay. This integration we are conducting, and 4 by alpha square is here. So that's why its integration is here. So now it is alpha cube by 2 minus alpha cube by 3. So this is now 4 alpha square, and this will be 2, sorry, not 2, rather alpha cube by, here it will be 3 only, please wait. Here, it will be alpha cube, and here it will be 6. So this is basically, uh, it will be 2 by 3 alpha. Okay. And surely this is not equal to alpha. Means expected value of this alpha cap, it is not equal to alpha. So this proves that this alpha cap, the estimated value of alpha, 2x, okay, it is not unbiased. It is not unbiased estimator for alpha. Okay, so this alpha cap, it is not okay. If the expected value of this alpha cap means this expected value of this 2x, okay, if it comes out to be alpha by chance, if it comes out to be alpha, okay, then we will say that this estimated value of alpha, it is MLE value also. Actually, it is unbiased also. Okay, I repeat, suppose if this comes out to be alpha, then this estimated value of alpha, okay, it is unbiased estimator of alpha and MLE value is already there. But here, since it is not equal to alpha, this is not equal to alpha, so we will say that this estimated value of alpha, it is actually biased. It is biased uh, estimate of alpha. Now, we have our sample from a population which is having Poisson distribution and sample size is n, and we have to find the MLE for parameter lambda. So L, it is pi fxi theta, and now this is pi e minus lambda into lambda raised to power xi and divide by xi factorial. Okay, and I1 to n. Okay, so what is our theta? The unknown parameter theta, it is lambda. Okay, and obviously this is I1 to n because our sample size is n. And now actually this small x1, x2, xn, okay, I have already mentioned that usually our sample observations, they are denoted by the small x size. So now what will be this? Actually, it will be e minus lambda into lambda x1 divided by x1 factorial, then e. So, sorry, x2 and x2 factorial and e minus and here xn factorial. So e minus n lambda and lambda summation xi. Okay, and here this xi factorial I1 to n obviously e raised to power minus lambda into e raised to power minus lambda into going on e raised to power minus lambda. How many times? N times. Okay. Then lambda raised to power x1 into lambda raised to power x2 into so on lambda raised to power xn means lambda raised to power x1 plus x2 plus xn. So that's why here it is this. Now x1 factorial into x2 into x2 factorial into x3 factorial so on to xn factorial. So that's why it will be product pi, okay, xi factorial. So this is L. So this is now a log of L, that will be log of E and this thing, then log lambda summation xi and minus log product xi factorial. Okay, so now this is minus n lambda. So this minus n lambda will be here. Into it will be log e. What will be log e? 1. And this summation xi, it will be here. Okay, so log e plus summation xi and into log lambda and minus this term as it is. Okay, so this is log of L. And now, what is log E? It is 1. So it is only minus n lambda. Okay, so this is now d by d lambda of log L. So what is its derivative? It will be minus n into 1 by lambda. Obviously, we will be differentiating with respect to lambda because here we are estimating lambda in such a way that it maximizes log L, and plus summation xi. And what is this derivative? It is 1 by lambda. And actually here it is this term is here product xi factorial, which is constant with respect to lambda, so its derivative is 0. So equal to 0. Okay. So now this will imply that n by lambda, this is equal to summation xi by lambda. Okay. Actually, I got my mistake. Actually, the derivative of this lambda is 1. So here it should be 1. Okay. So into 1. And now this is summation xi into 1 by lambda. So this is lambda. Here, what's the lambda? Summation xi upon n. Okay. And what is this thing? Once again, it is again our sample mean. So this is our estimated value. That estimated value of parameter lambda means sample mean. So sample mean is that estimated value of parameter lambda, which will maximize log L and hence L. Okay. Now here, just once again, actually, since this was the, if you observe that this is the first derivative, okay, the first derivative of log L with respect to lambda. If I conduct the wait, second derivative, so that will be d square by d lambda square of log L. So what is derivative of minus n? 0. And what will be derivative of 1 by lambda? It will be minus 1 by lambda square into what? Summation xi, I1 to n. Okay. So now this expression, it can never be negative, and because of this negative, it is always negative. Now, why this expression can never be negative? Now, first of all, what is lambda here? Actually, here lambda, it is the mean of the Poisson distribution, okay, or the random variable x, and it is also the variance, okay, the variance of the this Poisson distribution, okay, or variance of x. And since it's a variance, so it can never be, sorry, a lambda, yeah. So it can never be negative. And here, what are xi's? Actually, they are from Poisson distribution. Actually, in Poisson distribution, these xi's, they denote number of outcomes. If you have the knowledge about Poisson distribution, so in Poisson distribution, our random variable, okay, the random variable x, which is taking the values x size, sample observations, which are taking the values x size, they are actually our number of observations. Sorry, number of outcomes. They are number of outcomes, and since number of outcomes can never be negative, okay, we can't have minus 10 number of outcomes, minus 15 number of outcomes. So that's why even these are xis are the number of outcomes. So that's why this is never negative. So since this expression is never negative, but here it is negative, so it will become make it negative. So this proves the same thing, that the second derivative is negative here. Okay. So here we have a random sample from Bernoulli population. Obviously, Bernoulli population, its parameter is P, the probability of success. Okay. So what is Bernoulli population? What is the meaning of this probability of success? So for that, please do watch the lecture on unbiased estimator. Okay. So we have to find the MLE for this P. So please. So here L, it is nothing but product fxi theta. This is a product pxi 1 minus p1 minus xi I1 to n. So this is actually what is our theta here? P. The parameter theta is p, and this is the probability mass function of Bernoulli distribution. And now this 1 minus. So now here it is p raised to power summation xi. Why so? P raised to power x1 into p raised to power x2 into so on p raised to power xn means p raised to power uh, summation x1 xi, sorry, and 1 minus p. Look, here it is 1, here it is 1, here it is 1. So total n times 1, and minus, here actually minus x1, minus x2 going on minus xn. So it is minus summation, okay, summation xi. Okay, so this is L. So now log L, that will be log of P, and then, sorry, plus log of 1 minus P n minus summation xi, and summation xi log p means this term, it is here, and n minus summation xi into log of 1 minus p. Okay, so this term, it is here. So now d by dp of log L. So that is now summation xi into 1 by p, and plus n minus summation xi into 1 minus p, but into minus 1 also. Okay, the derivative of this term 1 minus p with respect to p. Okay, so 0. Actually, what is this function? It is log of fp, the function of some function of p. So its derivative is 1 upon fp. And what is this minus 1? Actually, it is nothing but f dash p, the derivative of fp. Okay. So now summation xi upon p, that is equal to n minus summation xi upon 1 minus p. Actually, this value, this term, we can come take this side. So now it is, if you see summation xi minus p summation xi, and this is np minus p summation xi. Just means what we say the cross multiply. Okay, means this term is here, and actually this term is here. Okay, so now actually this p summation xi cancels. So what is p now? Once again, it is 1 by n summation xi I1 to n. So now what is this? Actually, again, it is sample mean. Means the sample mean, it is the estimated value of p, the probability of success. Okay, so sample mean, it is the estimated value of that estimated value of p, which maximizes L or log L. Hence, it is MLE. Okay, one thing here in the last question, there was a one part. Yes, that here we have to find the variance of that MLE also here, find its variance means the variance of this MLE value. So what is that now? It is a variance of actually X bar. Why? Because this lambda cap, it was X bar sample mean. Now, what is the variance of the sample mean? It is sigma square by n. So what is sigma square by n? It is population variance. How this is equal to population variance? For that, the lecture number 1 of estimation. Okay. And now what is this sigma square, the population variance? It is lambda here. Okay. I have already told you that this sigma square, it is lambda. And once again, this lambda, since we don't have its exact value, exact known value. So that's why we will have its estimated value. And what is that estimated value? It is nothing but once again the sample mean. So what is this x bar by n? Okay, what is x bar? It is sample mean. And x bar by n, it is nothing but the variance of this MLE, which was being asked here. Okay. So thank you, dear. Thank you.